This video is the first of a series of videos in which I'll be summarising many aspects of a body of theory I've been building up over 20 years. In essence, it's a Kaluza-Klein theory of a higher dimensional spacetime, but it differs in many ways from existing Kaluza-Klein theories. I call it covariant compactification for reasons I'll explain. After 20 years, it's still a work in progress, but I've made substantial progress over this time in developing it into a theory of everything. Or perhaps, as the title says, that should be a theory of everything fundamental, as I'll explain. And indeed, while it's not yet complete, I'm convinced I've got further towards such a theory than the rest of physics research has achieved in the last 40 years. This series of videos is pitched at active physics researchers. However, there's plenty of material aimed at non-specialists on my website, Warped and Broken, and in my collection of work on Patreon. Until recently, superstring theory, with its D-brane and M-theory extensions, was considered the best candidate we have for a unified theory of all fundamental physics, incorporating quantum gravity. But recently, many physicists have begun thinking that it has not lived up to expectations. It's been a blind alley, or it's got bogged down in its swampland. Consequently, more attention is being paid to other approaches to quantum gravity. But even this is trying to push gravity into a quantum field theory paradigm, one which has many conceptual problems, including that QFTs generate infinities in calculating basic quantities relating to every particle in existence and have infinite zero-point energies. Dirac expressed serious discomfort with the procedure of renormalization, while Feynman said that the absurdities of the theory he had developed should be accepted simply because they resulted in the right answers. As we already have a perfectly good description of gravity as a curvature of spacetime, this doesn't seem logical. Nobody seriously challenges the notion of spacetime. It underlies both quantum field theories and general relativity. And we know curved spaces exist. The world we live on is a curved space. If space-time is curved, it has converging geodesics, and we experience this convergence as gravity. The equations governing this curvature have finite solutions, except perhaps at the very centers of black holes, points which are inaccessible and widely separated. So I'm exploring an alternative, extending the geometrization of gravity to the rest of fundamental physics. Clifford expressed the concept of this as long ago as 1876, and we'll see that his Clifford algebras have a starring role in the theory I'm outlining here. Paul Davies recounts this quote in his book Superforce, then gives an even more succinct expression of what I'm seeking, forces and fields themselves being explained in terms of geometry. So, where to start on building a comprehensive geometric field theory? Well, our current understanding of the universe is built on the twin pillars of general relativity and quantum field theories. General relativity is our archetypal geometric field theory, at least for the gravitational interaction itself. This is beautifully described as a curvature in four-dimensional spacetime. But matter is described classically, typically as point-like or rigid extended objects, or as fluids. If electromagnetism is included, it's described by Maxwell's field in four-dimensional form. And this does not describe curvature or similar aspects of geometry. Indeed, Einstein felt that his field equation was like a house made of two parts. While the left-hand side was made of marble, the right-hand side was made of low-grade wood. In quantum field theories, both fermions and the bosons which mediate interactions are described by fields. But these fields aren't taken as describing aspects of spacetime geometry, at least not in the established forms of these theories. A more promising place to start is Kaluza-Klein theories. These extend general relativity to spacetimes with more than 4 dimensions. This provides the possibility of gauge interactions being manifestations of higher dimensional curvature. However, matter fields are typically still not aspects of geometry. The question therefore becomes, how can we adapt Kaluza-Klein theories such that matter can become manifestations of space-time curvature? And the resulting theory both contains general relativity's description of gravity and reproduces the phenomena of quantum field theories. What I'm about to present goes quite a long way towards this. Covariant compactification is, therefore, a modified, revised Kaluza-Klein theory. While it draws on the work done on spontaneous compactification and Kaluza-Klein theories in the late 1970s and early 1980s, it differs in many ways from these models, as we'll explore in the final video. I should remark that I didn't start this research with the grand vision I've just described and the whole conceptual structure of it already figured out. These have emerged over time, as described in the one-page essay, Reflections on Building a Conceptual Structure, on my Patreon site. For an n-dimensional pseudo-Riemannian manifold, purely geometric arguments provide a way of decomposing it across a coordinate neighborhood into a product of factor spacetimes. Each factor space supports a local group symmetry. In the most general case, certain components of the Levi-Civita connection in appropriate coordinates can be identified with gauge fields. If one of the factor spaces has 3 spatial dimensions and 1 time dimension, the components of the Levi-Civita connection for that space, as usual, provide the coupling for tensor fields to gravity. At any point at which the gauge fields and gravity reduce to 0, other than a background curvature, we'll call a classical vacuum. This is a Cartesian product of a 4-dimensional Einstein manifold and a compact Einstein space. Reducing all the curvatures to 0 gives us what we call the decompactification limit with maximal symmetry, an n-dimensional flat spacetime. The most symmetric case with positive scalar curvature for the 4-dimensional spacetime, the classical vacuum is a Cartesian product of a de Sitter spacetime and an n-4 sphere. Covariant compactification has emerged from a careful consideration of spacetime symmetries and how they change under processes of compactification and decompactification. In the decompactification limit, space is at its most symmetric. An n-dimensional Riemann flat spacetime has Jacobian matrices which form the group GL-NR. Within this, there is a group of spacetime rotations SO1n-1, which has either 1 or 2 spinor representations. Compactification, which in this theory means going from the mathematical limit of a flat spacetime to a spacetime with the topology of our universe, breaks the GLNR symmetry and within it the SO symmetry. Note that this is not spontaneous symmetry breaking, in which the symmetries break as the energy in an experiment reduces. As these are spacetime symmetries, its curvature that distinguishes between the broken and unbroken symmetry regimes. Thus, the full symmetry is restored when we go from a curved universe, such as ours, to a flat one. Nonetheless, nonlinear realizations can be used to describe the broken symmetry. As we're developing a field theory, we're interested in fields on our spacetime. On any spacetime, field configurations can be decomposed into harmonics. For a flat spacetime or a circle, the simplest set of harmonics is the set of Fourier modes. For spheres of any dimension, the simplest set is the set of spherical harmonics. Covariant compactification is not a quantum field theory in the usual sense. Rather than assuming that we go from a classical theory to a corresponding quantum theory through a formal mathematical procedure of quantization, we assume that quantization is an emergent phenomenon. As we build the theory, quantum features will emerge. The idea of wave functions to describe matter was introduced by de Broglie and Schrödinger. Their papers, and another by Klein, showed how wave functions could be described by harmonics carrying quantum numbers. De Broglie drew on work by Bohr and Sommerfeld. He showed that how their results could be explained if electrons orbiting the nucleus of an atom had waves associated with them. He used the analogy of water in a ring-shaped channel to point out that a stable regime can only exist for an orbit if they have a wavelength such that the circumference is an integer multiple of the wavelength. This condition led to quantization of angular momentum around the orbit. Inspired by this, Schrödinger looked for functions which satisfied an Euler-Lagrange equation with the potential which would be experienced by an orbiting electron. He pointed out that, expressed in spherical polar coordinates, each such function would be the product of a spherical harmonic and a radial function, and went on to find these radial functions. The spherical harmonics, which were already known, are specified by two quantum numbers, while the radial function carries a third. Late the same year, Klein pointed out that if one accepted Kaluza's notion of a fifth compact dimension, the phase of complex wave functions had a natural interpretation, and the momentum associated with displacements around this dimension would be quantized. He observed that if the quantized momentum for a charged particle was shown to be proportional to its electric charge, the normal equations of motion implied that it followed a geodesic in the five-dimensional spacetime. This, he suggested, could be the origin of quantization of electric charge. These quantum numbers, along with the energy momentum quantum numbers, are associated with diffeomorphisms on spacetime. I'll explain this in the next two videos. The energy momentum quantum numbers are associated with translations in a flat or near flat spacetime. They all commute, and if the spacetime is infinite, they form a continuous spectrum. Rotations on a sphere, on the other hand, form a compact group. They do not commute and have discrete quantum numbers. These quantum numbers will appear in the theory if we have field configurations decomposed into the corresponding harmonics. Now, recall that we want matter to be described in terms of geometric fields. An idea of what this means can be found in a paper by Martin Tam from 2023. This considers whether a rotating patch of curved spacetime could be observed as a particle with spin. There are flaws in his analysis, but the idea is intriguing and certainly fits our requirements. This new conception of the universe keeps the picture of gravity found in general relativity, but changes the picture of matter. It goes from one in which, as Wheeler said, matter tells space how to curve and space tells matter how to move, to one in which matter is curved spacetime. This gives a new interpretation of Einstein's field equation. It's not telling us the curvature that's induced by a matter distribution. Instead, it's saying that curvature and matter are one and the same. It's an identity providing a translation between the curvature picture in geometric units and the matter picture in units of matter kinematics. Note that in this picture, conservation of energy momentum is conservation of geometry. The contracted Bianchi identity, which arises purely from algebraic considerations of geometric quantities. The picture that we're getting is that we can attribute quantum numbers to curved spacetime if we decompose a geometric quantity into harmonics. The question then is which geometric quantity? It turns out that the appropriate field is the square root of the absolute value of the metric determinant, which we'll denote in this way. And here's why. Any Riemannian or pseudo-Riemannian spacetime looks flat at small enough distances. Around any point, we can define a coordinate basis xi, which becomes orthonormal at that point. The volume of an infinitesimal hypercube at this point is simply a product of the coordinate differentials in this coordinate system. If we transform to any other set of coordinates ui, we can rewrite this volume element in this form. The Jacobian determinant here is precisely the square root of the absolute value of the metric determinant in u coordinates. This quantity therefore gives us a measure of the volume contained in an infinitesimal element of space in comparison to the volume in flat spacetime. Having the volume element also allows us to perform integrals in any coordinate system. This is important because in covariant compactification, matter is not viewed as composed of point-like particles. Instead, it's viewed as composed of regions of spacetime in which the curvature differs from that of the classical vacuum. The quantum numbers of any such region relate to the region as a whole. They are not fields themselves. To get them from a field describing the geometry of that region, we need to integrate over the volume of that region. For example, as we shall see, three-dimensional hypervolume can carry a momentum, a single vector for the whole hypervolume. The field we need to integrate is therefore a vector density. Under a change of coordinates, there's a factor in the transformation law for the vector density, which is the reciprocal of the factor by which the volume element is transformed. This ensures that the momentum vector transforms in the appropriate way for a vector. The simplest such integral is a scalar, the integral of the volume element over the volume, that is, the volume of the spacetime region itself. Now, while root mod g isn't invariant under changes of coordinates, it has a single component. That is, in a given coordinate system, it has a single value everywhere we can use those coordinates. If we have a spherical n-dimensional hypervolume in our spacetime, we can decompose root mod g into spherical harmonics. Under the action of an orthogonal group of diffeomorphisms on the hypervolume, these are mapped into each other in multiplets. The action on each multiplet is a unitary representation of On plus 1. The smallest multiplet in the series is a singlet, a constant value over the n sphere. The next smallest is the spinor multiplet, or for an even value of n plus 1, the direct sum of the two spinor representations. All of the other multiplets can be constructed from this by taking outer products. We therefore return to our highly symmetric classical vacuum. A de Sitter space has a natural time coordinate, sometimes known as cosmic time. At a given moment in cosmic time, our spatial universe, in its classical vacuum state, would be the Cartesian product S3 cross Sn-4. For a realistic universe, there is additional curvature which is manifested as matter and its interactions. In general, on such a perturbed geometry, the factor spaces are no longer geodesically complete. This makes determining the exact harmonics of the spatial universe difficult. I haven't tried to do this, and I'm not certain how one would go about it. I suspect it might involve mathematics developed over the late 1970s, 1980s, and perhaps since. Maybe that of Karen Uhlenbeck and her collaborators. But I've yet to get to grips with this. However, the harmonics on such a spacetime will, to a good approximation, be a product of those on S3 and those on Sn-4. We therefore expand root mod G as such a product. The expansion includes spinors of SO4 cross SON-3. Now it's known from the work of Wigner that massive unitary representations of the Lorentz group, or more properly, Poincare group, have three quantum numbers: their rest mass, their total angular momentum, and the third component of their angular momentum. It's only the first of these that distinguishes the three generations of fermions. Let's first fix the rest mass and consider just one generation of fermions. If we count up the various combinations of quantum numbers, as we'll see in a later video, we can accommodate all the states into one 32-component spinor. This can be written as a product of a 4-spinor and an 8-spinor. This implies that the number of extra dimensions is 6, 7, or 8. If we choose 6, then the gauge fields in the theory, as we'll see later, are SU4 gauge fields. This SU4 gauge symmetry contains the SU3 gauge symmetry of the strong nuclear force. All the quantum numbers for the generation are compatible with this arrangement. The fermions themselves can break the SU4 symmetry down to SU3 cross U1. The spinors will have factors which are functions of the three spatial coordinates corresponding to the familiar three dimensions of space at a specific moment of cosmic time. However, we want to consider these from the frame of reference of an observer who is not at rest with respect to cosmic time. To do this and get a function of all four of that observer's spacetime coordinates, we would need to perform a Lorentz boost. This is a part of the theory I haven't yet researched. However, it's worth noting that SO4 has two two-dimensional spinor reps, making up a four-dimensional sum rep. Its Clifford algebra has 5 gamma matrices, and the gammas in its direct sum rep, its Weyl rep, are those of the Lorentz subgroup in the Dirac rep. Consequently, it looks likely that a 4-spinor of SO4 in the Weyl rep is also a Lorentz spinor in the Dirac rep.